Good morning friends, welcome to the second module of our course where we are going to discuss about the thermodynamic property relations. In previous week we have basically reviewed the fundamentals of thermodynamics over 4 lectures, where starting from the basic definition of a thermodynamic system we went on to discuss the concepts of entropy and exergy. And there you have learned that for a proper thermodynamic analysis of any system, open or closed, we need to apply both first and second law of thermodynamics, because first law provides an energy balance, thereby relating the change in the stored energy of a system to the corresponding energy interactions between the system and surrounding. However, first law fails to provide any direction to the process, and therefore only reliance solely upon the first law may lead to the situation like a PMM2. And therefore, we also have to apply the second law of thermodynamics to understand the realistic direction of any particular process, and also to understand the theoretical limit of operation of any thermodynamic device, a heat engine or reverse heat engine or any other similar kind of thermodynamic device, for which using the concept of second law of thermodynamics or maybe the exergy, we can define a second law efficiency. Thereby we shall be able to understand the performance, or able to compare the performance of any device in terms of the maximum possible performance instead of some ideal performance. And there, in course of those thermodynamic analysis, the application of energy concepts or exergy balance, we had to make use of several kind of properties. And this particular module we are going to discuss about the options of identifying some of the most crucial properties that we have to make repeated use of in course of thermodynamics. Now, the previous lecture, or I should say the previous week, the 4th lecture of module 1, I finished by mentioning about the balanced equations of thermodynamics, where for the application of first law we have to apply the conservation of energy principle, whereas for performing a second law analysis we can write either entropy balance or exergy balance. I did not spend too much time on this because I want to spend just couple of minutes more on that now, and therefore I just decided to go through very quickly there. Let us just start from that particular point onwards. So, we know that for any generalized thermodynamic system, if we want to perform a first law analysis, we can write an energy balance or a principle of energy conservation. And for an infinitesimal process, the principle of energy conservation can always be written as rate of change of energy of the system to be equal to the rate of heat transfer or rate of heat supplied to the system minus the rate of work done by the system, plus if there is any mass interaction involved, then the amount of energy supplied with the mass. It is very much possible, particularly in case of open system, that the system may involve multiple type of mass interactions and similarly multiple types of heat and work interactions. And also work interactions, quite often we try to divide into two convenient forms. One is the moving boundary work and other is the any other kind of work such as electrical, surface tension, or anything related to kinetic or potential energies, whatever may be the other form of work that we generally like to group here, just keeping the moving boundary work separately. And moving boundary work, we know for an infinitesimal small process can be represented as PDV. So, the work interaction can be represented as PDV plus del W other. So, if you take that form, then we can often represent this equation as summation of all kinds of heat interaction that is possible, J being some subscript and which indicates the heat interaction that we are particular interaction that we are talking about, minus the moving boundary work associated with that particular process, plus summation over all other kind of heat interaction that may be there, or I should say work interaction, plus all possible kinds of mass interactions. Here the direction of mass transfer is taken to be into the system. If we are talking about mass flowing out of the system, then there will be a negative sign coming in. Now, let us just go into the expression for this dE. So, we know that the rate of change of energy for a system can be represented as a combination of 3 parts: the kinetic and potential energies, which form the macroscopic part. So, this is kinetic and this is potential, plus the microscopic part in the form of internal energy. And if we are talking about a stationary system, which is the case for most of the thermodynamic system that we practically deal with, the changes in kinetic and potential energies can be considered to be 0. And also in most of the cases you will find that the change in internal energy is so much that the corresponding change in kinetic and potential energies can often be neglected. And in that situation, this equation can be represented as just du, where this energy has only the internal energy part now, equal to the right hand side is retained as it is. So, the summation of all possible heat interaction in the direction of q taken to be into the system minus the moving boundary work plus any other kind of work interaction which can be there in certain special cases, plus summation of j del m j theta j, all possible kinds of mass interaction. This is a general equation. There can be several possible simplifications of this equation, like if you are talking about a closed system, then this part will not be there. If we are talking about an adiabatic system, then this part will not be there. If we are talking about a simple compressible system, that means it can produce work only in the form of moving boundary work, then this del W other will not be there. But of course, I have striked out 3 does not mean that all these 3 will go off. Each of them, each of the 3 can be retained or may not be. Like in certain situations, if there is no moving boundary work, then this PDV work may also go off. So, while there are 4 terms, I am just going back to the original equation, there are 4 terms on the right hand side, but all 4 are hardly present in a practical situations, and we have to choose whichever we need to talk about. But the left hand side is du for a stationary system, which is always retained. Now, let us go to the second law analysis based upon the entropy or exergy. So, we can perform second law analysis based upon entropy generation concept or entropy balance, and similarly by exergy balance. So, if we perform an entropy balance, then as we have written in the previous lecture, so total change in entropy of a system can be considered to be the entropy coming in. So, the summation of all the sources of entropy into the system minus all sources of entropy moving out of the system plus entropy generation. Here we are putting a del sign in front of entropy generation because that depends on the process. If you are talking about a reversible process, the entropy generation will not be there. Or we can write this equation as, so considering all possible types of entropy flowing into a system or out of the system, we can have entropy coming in with heat transfer. Again, there may be several possible types of heat transfer. There is no entropy transfer with work transfer, whether it is moving boundary work or any other kind of work, there is no entropy transfer, but there will be entropy transfer with mass. So, del m j small s j, where small s is the specific entropy of that corresponding mass plus the entropy generation part. So, once we have knowledge about the amount of heat interaction and mass interaction the system is subjecting, we can easily calculate this term and this term. Again, if we are talking about a closed system, then the mass delta term will not be there. If we are talking about an adiabatic situation, the first term will not be there, whereas if we are talking about a reversible process, then the entropy generation will not be there, but the left hand side is ds, which is a change in entropy, which is always there. Similarly, if we talk about the exergy balance, then the change in exergy for a system can, I am directly writing the equation now, that can be the amount of exergy coming with the heat. So, with the heat we know that we should write this one as 1 minus T naught upon T j to del q j, where T j is the temperature at which this del q is j is supplied, plus or minus all the kinds of work interaction the system may be having, that is PDV plus summation of the other kind of work interaction plus all possible kinds of mass interaction del mj psi j minus the exergy destruction, which is again dependent on the process. Now, what is the expression for this psi? or if we just think about the expression for this x, the change in the exergy of a system, then how we can relate this? If you remember the way we have represent the change in exergy for a stationary system, then we know that this dx can be represented as du plus pdv minus tds for an open system, whereas for a closed system, whereas for an open system it was dh minus tds. So, now look at all these expressions and you will find a particular trend that in all the cases the terms that are appearing on the right hand side of the equations, that generally depends upon the interactions that we are talking about, like the heat interaction or work interaction or mass interactions, which we generally can calculate by considering the system surrounding exchange that is happening. The specific nature of the entropy generation or exergy destruction, that can be calculated again by considering the nature of the process, and these two are related to each other. So, if we calculate one, the other is also known. However, the terms which are appearing on the left hand side, that which are actually properties of the system, like on the left hand side we are getting terms like the change in internal energy, change in entropy. If we are talking about the exergy, then we are getting terms like change in enthalpy, something like this. And therefore, we are mostly trying to express this equation ultimately in terms of the change in certain extensive properties like internal energy or enthalpy or entropy. But the problem is there, these three properties that I have summarized here, none of them can be measured directly. Just think about a real life situation. If we want to understand or identify exact physical state of a system, then you can easily calculate the pressure, temperature, volume, mass, or using the value of volume and mass you can calculate specific volume or maybe density. So, these are certain parameters which can be calculated, or I should say measured very easily. However, the basic conservation equations of thermodynamics or basic balance equation of thermodynamics we are getting not in terms of those properties, rather in terms of these three properties, the changes in internal energy, changes in enthalpy and changes in entropy, but none of them can be measured directly. And that is where we need to develop certain kind of property relations where we can represent the change in these parameters in terms of the measurable parameters. So, in common thermodynamics we generally can classify properties in two different manners. Of course, one type of classification is intensive and extensive, but here we are talking about the practical sense. So, a group of parameters like temperature, pressure, specific volume, mass, etc. can be measured very easily, whereas parameters like internal energy, enthalpy, entropy, etc. can't be measured directly. So, the objective of this particular module, that is thermodynamic property relation, is to develop certain relation where we can represent this second group in terms of the first group, or we want to represent or develop mathematical relations using where we can represent the internal energy and enthalpy and entropy or this kind of other properties in terms of the measurable quantities like temperature, pressure, specific volume, etc. And a second thing of importance here is that we are, truly speaking, we are not bothered about the absolute value of U or S. We are trying to identify the change in this internal energy or change in this entropy or maybe the change in this enthalpy. So, what we are trying to develop now is relations not to have perfect value of these quantities, rather to get the expressions of the change of them, that is changes in internal energy or changes in enthalpy or changes in entropy, and similar parameters which we are trying to develop in this particular module. For that or before going to the derivation of that, I would like to go back to the thermodynamic property. Now, you know the definition of property, which is any quantifiable characteristic of a system, and so you may be thinking what else to discuss about that. You know the definition of property, you know different types of classifications, you already have idea about several kinds of properties and how to use them in relations. We are not talking in thermodynamic point of view, rather we are trying to get a mathematical perspective of a thermodynamic property. Let us consider a parameter z which is a function of x and y. Now, here x and y represent two intensive independent properties. X and y represents two independent extensive properties. Just remember the phase rule that we discussed in the very first lecture. As per the phase rule, the state of a simple compressible system can be defined in terms of two independent intensive properties. That is, once we specify two independent intensive properties, all other properties of the system at that particular state can be calculated. So, in this module actually we are looking to calculate those property relations or certain of those property relations. So, here x and y represents two independent intensive properties, and we are trying to develop a way of understanding whether z is a property of the system or not. So, if we differentiate on both sides, we can write z to be something like dou z dou x with y constant dx plus dou z dou y with x constant dy. It is a simple partial differential form. Let us write this as m dx plus n dy, where m is the first partial differential, that is dou z dou x with y constant, and n is dou z dou y with x constant. Now, if z is a property, then what should be the mathematical relation between m and n? If m, or I should say z, is a property, then it is a very standard mathematical principle that for z to be an exact function of x and y, or dz to be a exact differential, then we need to have dou m dou y with x constant to be equal to dou n dou x with y constant, because then only we are going to have dou to z and dou y dou x to be equal to z dou x dou y. So, this is the condition for z to be a perfect function or exact function of x and y, and that is how we can identify any unknown parameter whether that is a property or not. Once we have specified two independent intensive properties x and y, and then we have represented z as a function of this x and y, then using this simple principle we can understand whether z is a property or not. Because if z is a property, then as per the phase rule it must be an exact function of this x and y, provided x and y are independent and intensive. Let us see some examples. This is our first example where we have taken dz equal to p dv plus v dp, and it is given that p and specific volume, that is small v, are independent and intensive properties. So, we compare with this. So, here m is representative of this p, n is represented by this small v. Just remember the form that we had there. We had dz equal to m dx plus n dy. So, we are trying to compare with that form. So, we got m and n. So, your x equivalent to x here is small v, and equivalent to y here is p. Then your dou m dou y with x constant will be dou p with v constant, that is equal to 1, whereas now if we take dou n dou x with y constant, then we have, just putting the expressions for n and x, we have dou v with p constant equal to 1. These two are equal to each other, and therefore, we can say that this z is a property of the system. Let us take a second example. So, dz equal to p square dv minus v square dp. So, if we compare in this one, your m is equivalent to p square, n is equivalent to minus v square, x is equivalent to v, and y equivalent to p. So, your dou m dou y at x will be what? Will be equal to dou p of p square with V constant, that is equal to twice of P, and dou n dou x with y constant will be equal to dou V of n is minus V square, P constant is equal to minus of twice V, and these two are not equal to each other. So, Z is not a property, as it is not satisfying the phase rule, or I should say it is not is the exact function of this P and V. A third example, here actually the differential form is not given, rather Z as a function of P and V is given. So, first we have to convert this one into the differential form, into a form like this. So, we write this as 1 upon R to P plus A upon R into V minus B. Now, differentiate both sides with sides. So, we have Zz equal to, so we have V minus B by R dP plus 1 by R into P plus A by R dV. If we compare with the exact form now, or the standard form, here M is equivalent to V minus B by R, N equivalent to 1 upon R into P plus A by R. Here is your X is P and Y is equivalent to V. So, if you calculate dou M dou Y maintaining X constant, then what will be that? Your Y is V, so it will become 1 by R, and similarly if you calculate dou N dou X keeping Y constant, your X is P, so if you differentiate N with respect to P, then again you are going to get 1 upon R. So, these two are equal, that means here Z is a property. This way we can identify any parameter. Once we know the relation of this Z with X and Y, then we can easily identify if it is a property or not. This particular formulation we are going to make use of in today's work. Next, I would like to introduce you the concept of thermodynamic potential. The four symbols that I have listed here, two of them are already known to you, U and H, but other two, F and G, these four together are called the thermodynamic potentials, because they represent the energy of a system under different situations. Here U is the internal energy, and we know that this is the manifestation of the molecular activity of a system, or you can say U is a representative of the energy required to create a system by virtue of the molecular activities and molecular orientation. Then what is enthalpy? We know to get enthalpy we have to add this PV with this H, or sorry, with U, or if we write in here all symbols are shown in extensive sense, if we write in intensive sense, then we know that H is equal to U plus P into specific volume. So, with internal energy we have to make, or we have to add this flow work, and this flow work can be visualized as a work which you need to make some space for this particular system. So, enthalpy is representative of the amount of energy needed to create the system plus the amount of energy required to make some space for the system. This is enthalpy. Then what about this capital F? That is called the Helmholtz free energy. As shown here, it is a Helmholtz free energy, and it is represented as U minus Ts. Just follow these symbols. Once we subtract minus Ts, then from this internal energy we get this Helmholtz free energy. Or in intensive sense, if we write small f is equal to small u minus T into small s. In certain textbooks a symbol small a is also used, like the book that we are mostly following in this course, the book of Sengel and Bowles, that actually uses small a as a symbol. Now, Helmholtz free energy means from the internal energy part, that is the amount of energy needed to create the system, you have to subtract this Ts portion, and this Ts can be viewed as the energy that we get from the system's environment by heating. That is, once the system is created, because of its thermal non-equilibrium in the surrounding, some heat can flow from the surrounding to the system to get the thermal equilibrium back. Here S refers to the entropy of the system. So, this Helmholtz free energy is U minus Ts, and you can visualize this as the amount of energy needed to create a system minus the amount of energy that the system is getting from the environment. And finally, G. So, what will be the expression for the G? Here you have to subtract Ts from H. So, this G in intensive sense is equal to H minus Ts, that is equal to U plus PV minus Ts, that is Gibbs free energy. So, expression for your Gibbs free energy is then the U minus Ts plus PV. So, U is the amount of energy needed to create the system, plus PV is the amount of energy needed to make space for the system, minus Ts, which is the energy the system is getting from the environment. So, these four together are called the potential of the system. Let me summarize this one. H is equal to U plus PV, then F is equal to U minus Ts, and G is equal to H minus Ts, that is U plus PV minus Ts, and these four together are called the thermodynamic potentials of a system. In the analysis that we are restricting ourselves, we generally have to use U and H, but in certain situations, particularly when talking about the chemical thermodynamics, this Helmholtz free energy and Gibbs free energy also comes into picture, because there this amount of energy the system is receiving from the surrounding becomes important. Now, the one that we are looking to develop, the Maxwell's relation. Maxwell's relations are a group of equations to relate the partial derivatives of pressure, temperature, specific volume and entropy to each other for a simple compressible system. Look at the four properties we are talking about: pressure, temperature, specific volume and entropy. Now, out of this, the first three, pressure, temperature and specific volume, as I mentioned earlier, can be measured very easily. For most of the situations, using simple instruments we can measure each of the three. However, entropy is the one that we can't measure, that is only a theoretical definition. So, the Maxwell's relations actually serve or provide an option to relate the change in entropy in terms of the changes in these three quantities by relating the partial derivatives of these four quantities. And to develop the Maxwell's relations, there will be four equations that we are going to develop. We have to make use of the four thermodynamic potentials that I mentioned in the previous slide. Now, what was the first thermodynamic potential? That was U. Now, I would like to take you back to the third lecture of this course, where we developed a couple of TDS relations. Do you remember those TDS relations, or so called Gibbs equations? I hope you remember. The first equation was TDS is equal to du plus P dV, that is du equal to TDS minus P dV, or if we write in terms of extensive properties, du equal to T d capital S minus P d capital V. That was the first TDS relation. What was the second TDS relation? Your TDS relation was TDS equal to dH minus V dP. So, we can separate H out, the second potential, as TDS plus VdP, or if we write in extensive sense, d of capital H is equal to T d of capital S plus capital V d of P. So, we have got two equations representing the rate of change in the corresponding two potentials. Now, let me use the definition of the Helmholtz energy now. Now, what was your definition for Helmholtz energy? You had A equal to U minus Ts, that is dA equal to du minus Tds minus SdT. Now, du minus Tds we can take from this equation to represent, actually I am more confident of writing this F, writing in terms of A, but we are using F, so let me stick to that. So, d of this small f now becomes du minus Tds, this quantity we are replacing using minus P dV minus S dt, or in extensive sense d of capital F is equal to minus P d of capital V minus capital S d of T. So, we got now an equation representing the change in this Helmholtz free energy, and hopefully you have understood what we are going to do next. We are going to use the expression for the Gibbs energy, Gibbs free energy. So, G is equal to H minus Ts, dG is equal to dH minus T ds minus H dt. Now, this dH minus T ds can be you replaced by whatever we are getting from there. So, we get dG equal to small v dP minus S dt. That is, in extensive sense, change in the Gibbs free energy is equal to capital V dP minus capital S dt. So, here we have now 4 equations representing the change in each of the thermodynamic potentials. So, these are the 4 equations that we have now. Here I have again represented each in their corresponding intensive sense. Now, as internal energy is a property, then if this small s and small v are independent intensive properties, they are intensive, of course, they are written in intensive sense, and if they are independent of each other, then we can use the previous principle. So, I am rewriting that dz equal to m dx plus n dy, and if z has to be a property, we know that the principle is dou m dou y at x should be equal to dou n dou x at y. So, here what we have as, here your m is equivalent to t, n is equivalent to minus p, x is equivalent to s, and y is equivalent to small v. We know that internal energy is a property of the system. So, we can directly write now using the principle that dou t dou v with s constant to be equal to minus of dou p dou s with v constant. That is the first Maxwell's equation. Now, the second one. In the second case, we have m represented by t and n represented by small v, x represented by small s, y represented by p. So, from there what we can write? We know enthalpy is a property, so you can directly write this as dou t dou p with s constant is equal to dou v dou s with p constant. Look at the third one, which is the one involving the Helmholtz free energy or change in the Helmholtz free energy. Here m is equivalent to minus p, n is equivalent to minus s, x is equivalent to small v, y is equivalent to t. So, from there what we can write is minus of dou p dou t with v constant is equal to minus of dou s dou v with t constant. The minus sign we can omit from there. So, this is the third Maxwell's equation. So, we have got 3 Maxwell's equation now. The first one from the internal energy expression, second one from the enthalpy expression, third one from the Helmholtz free energy expression, and the one from the Gibbs free energy expression, where we have m equivalent to small v, n equivalent to minus of small s, x is equivalent to p, y equivalent to t. So, if we write there, we have dou v dou t at constant p is equal to minus of dou s dou p at constant t. So, this is the fourth Maxwell's equation. These are the 4 Maxwell's equation where we are relating the partial derivatives of this 4 quantity: temperature, pressure, specific volume, and entropy. This is a summarized view, just equations I have organized in a different pattern. So, we have dou t dou p at s equal to dou v dou s at p, then we have dou p dou t at v equal to dou s dou v at t, dou t dou v at s equal to minus dou p dou s at v, and dou v dou t at p equal to minus dou s dou p at t. Seems complicated, right? Because you have to remember these equations. Of course, you now know how to derive them, you can easily derive them, but there is actually a way of remembering these equations. I am just writing all the corresponding 4 Gibbs equations with that, or so called the Gibbs-Newton equation for the 4 thermodynamic potentials that we have. So, I have the 4 expressions. Actually, it is not that these two are corresponding to each other, because here we have changed the order of the Gibbs equations and also the Maxwell's equations. We are just writing the equations as per our convenience. So, to get an idea about how to remember these equations, we make use of something that is known as the Maxwell square or thermodynamic square or mnemonic. Just see how we have written them in a square form. We have basically made a 9 by 9 grid inside a square, and the middle one is empty, or the central one, and other 8 have been occupied by the 8 terms that we are talking about. Here the middle ones are the 4 potentials and the corner ones are the 4 properties that we are using in these Maxwell's equations. Here everything is written in extensive sense, but commonly we use the intensive notation, that is what I shall be doing. Before I am going to tell you how to use this, it is important to present the numbers in the particular order that is shown, because otherwise there is no point remembering this. You have to represent the symbols exactly the way that is presented there. And there is several kinds of mnemonics by which you can remember them. This is one of the sample. A good physicists have studied under very fine teachers. So, good, the G is there, and then we go in the clockwise direction, that is we go in this particular direction. So, we have G, P, H, we have G, P, H, S, U, V, F and T to finish. So, just repeating it once, good physicists have studied under very fine teachers. There is nothing in between. So, this way we represent by going in the clockwise direction and making use of this particular mnemonic. This diagram I have taken from Wikipedia, but similar kind of diagrams you can get from several other sources also, and sometimes even in textbooks also. Now, how to make use of? Let us first try to develop the Gibbs equations, that is equations for the thermodynamic potentials using this. Let us take the example of this internal energy U. So, this is your internal energy. To write the expression for the change in internal energy, we have to see the two corners opposite to that. Means there are two variables on either side of the U. Do not look at that, look at the other two corners, that is this one and this one. These two will be the potentials, or I should not the potentials, I should say this should be the coefficients of the expression. That is, your expression will be of the form minus P into d of something plus T into d of something. So, minus P and T, that is the terms which appearing in the opposite corners, will be the two coefficients. The terms which appear on the left hand side, like the P and S or left hand side corners, there generally we have this minus sign. Now, what will be going into the differentials? Into the differentials, we shall be using the terms which are adjacent to the U. So, for P, we have to, when the coefficient P we already have, like here, this particular part, to get this we have to go to the diagonal, the one opposite to P, which is V. So, write V here. Similarly, for getting T, we have to go to the opposite of this, which is S. We generally do not consider the negative sign while writing the differentials. So, it is TdS minus PdV, if I write in proper sense, TdS minus PdV, which is this equation. Let us take another sample. Let us consider the F. So, if we want to consider or write this expression of dF, then what will be your coefficients? To check the coefficients, go to the two corners which are opposite to this. So, this is one of the corner and this is the other corner. So, you know that these two will be the coefficients. So, one of the coefficients will be minus S into d of something plus, okay, So, minus p you have into d of something. To identify what goes inside this, then for S you have to go to the opposite corner, that is it will be dt. For p you have to go to the opposite corner, that will be equal to dv. Look at, this is the expression, df is equal to minus p dv minus s dt. Can you work out anything else following the same pattern? So, if we want to write say for dg, what it will be? For g you have to identify both the opposite corners. So, opposite corners are v and s or minus s. So, you will be having v into d of something minus s into d of something. For v, what will be there? Opposite to v is minus p. Now, while writing differentials we do not consider the minus sign. So, it will be v dp minus s dt, which is this expression. So, this is how we can make use of the square to develop the expressions for all these 4 Gibbs-Newton equations. Now, what about the Maxwell's relations? The first 4 that are more complicated to remember. To develop these relations, let us just drop the minus sign for the moment. So, let us consider this to be plus s and plus p. So, the rule of developing these relations is we have to go either in the horizontal direction or in the vertical direction, and let us pick up say p. So, and we move in the horizontal direction from p. Then we shall be writing dou p dou t with something as constant, that will be equal to, go to the other arm. So, parallel to p is s. So, we shall be going here also in this direction, it will be equal to dou s dou v. And what will be the constants, or I should say the subscripts? For p, the first one that we have written, we have started with p, so we have to check the diagonal to that. So, subscript will be small v. Similarly, for s, we have to go to the diagonal, which is t. Have you seen this relation? This is the one that we are talking about. Similarly, if we for developing the second one, we can again go in the horizontal direction, but now starting from the right moving to the left. So, for the bottom row we have dou t dou p with what will be the constant? The one in the diagonal of t. So, that is s, that will be equal to what? Can you guess? We are moving along the horizontal line from the right to the left. So, we have started with t and moved to p. So, go to the parallel row, which is dou v dou s, and the subscript will be the one opposite to v, or the diagonal opposite to v, which is p, which is the first relation. So, this way we can develop or recover 2 of the relations. Now, how to get the other 2? To get the other 2, we have to make use of the verticals. Let us move from this, from p to s, similarly from t to v. Let me erase this to make some space here. So, we shall be writing dou p dou s. Now, you know what to put in the corner. So, we are starting with p. So, diagonal opposite is small v, that will be equal to dou t dou v, and diagonal opposite to t is s. But one exception, when you go in the vertical direction, to put a minus sign before that. So, what do you have here? Have you got this relation? This is the relation that we are talking about. Similarly, now if we come from top to bottom, that is starting from s moving to t, similarly from v moving to t. So, we have dou s dou p with t is equal to minus dou v dou t with p, and this is the fourth relation that we have developed. So, if you make judicial use of this square, you can easily recover each of the 4 Gibbs equation and the 4 Maxwell's equation, and can subsequently can make use of that. Try to remember this equation. I have provided you enough options of remembering this, like this is one of the mnemonics that we generally follow, and using this then you can only thing that you have to remember, or only two things, one is this mnemonic and then moving in the clockwise direction. Once you go in the clockwise direction, starting with G at the bottom, you can easily get this. So, this is the, or these are the Gibbs equations and subsequent Maxwell's relations, where we are finding an option of relating the derivatives of entropy with temperature, volume, specific volume and pressure. But we started with the objective of developing relations of du, df or du, dh and ds. Of course, Gibbs equations are there, but that, like if you see here, the equation for du also incorporates ds. Similarly, dh incorporates ds. So, now we have to make use of this Maxwell's relation to update this Gibbs equation, so that we can replace this ds and write this only in terms of Tp and specific volume. So, let us try to develop some generalized relation for changes in internal energy. For that, let us assume U to be a function of T and V, that is temperature and specific volume are the two independent intensity properties that we are choosing. So, we can write du equal to dou U dou T and V dt plus dou U dou V with T constant dV. Now, what is your dou U dou T? If we apply the first law of thermodynamics for a closed system, closed stationary system, we know that du is equal to del Q minus del W. We have written everything in per unit mass sense, and if we are talking about a simple compressible stationary system, that is equal to this P dV. If you separate out del Q from there, del Q will be what? Du plus P dV from this. And if we are talking about a constant volume process now, then there is no moving boundary work, which is equal to 0, which gives del Q equal to du, and del Q during a constant volume process can be represented as Cv dt, which will be equal to du. That means dou U dou T at constant volume can be represented as Cv, the coefficient or specificity at constant volume. So, this is equal to Cv dt plus dou U dou V T dV. Now, we take entropy as a function of the same two intensity properties T and V. So, we can write ds is equal to, following the same pattern, dou S dou T at constant V dt plus dou S dou V at constant T dV. Now, we know the TdS equation as du equal to TdS minus P dV. So, if we put this expression for ds there, so we have T into dou S dou T at V dt minus, or I should say plus, T into dou S dou V at T minus P dV. I am doing several calculations here. My suggestion is you keep on doing parallel to me, so that you can immediately grasp what I am doing. Of course, you do not have the option of asking me to repeat anything directly, but you can pause the video and go back wherever you have some confusion. Now, you have one expression for du here, another expression for du here, and you can see on the right hand side, here your coefficients are terms are dt and dv. Similarly, here also you have dt and dv. So, if you compare the coefficients of dt, then you can write Cv is equal to T dou S dou T at V, or dou S dou T at V is equal to Cv by T. This one we shall be using in the next lecture when we develop generalized relations for entropy. Let us take the second part. So, we have dou U dou V at T, that is equal to T into dou S dou V at T minus P. Now, we make use of this particular Maxwell's relation, and accordingly we can substitute this dou S dou V at T as dou p dou t at V minus P. So, combining this with the original expression, we now have du equal to Cv dt plus T dou p dou t at V minus P dV. So, what we have now, look at the left hand side, here we are talking about the changes in internal energy or specific internal energy, whereas what we have on the right hand side, we have specific volume or specific heat at constant volume, I should say, Cv on one side, and we only have temperature, pressure and specific volume. So, if we know the PVT relationship of any particular substance, something like an equation of state, ideal gas equation of state, etc., you can easily calculate the changes in internal energy using that knowledge and also the knowledge of this Cv. If we integrate this, say we are talking about a process moving from 1 to 2, then you can easily calculate the change in internal energy U2 minus U1 as integral T1 to T2 Cv dt, where T1 and T2 are the initial and final temperature respectively, plus integral V1 to V2 T dou p dou t at V minus P dV. We shall be doing some exercise about how to use these relations in the next class, but before that you try to repeat these calculations on its own just to develop this particular relation for this changes in internal energy. Let us just follow the same procedure to quickly develop the relation for the changes in enthalpy. Here we shall be considering H to be a function of T and P. We are following similar procedure, so I am trying to do a bit quickly. So, dH is equal to dou H dou T at P dt plus dou H dou P at T dP, and again we can make use of the first law of thermodynamics for a simple compressible closed system, where we can write del Q equal to du plus del W equal to du plus P dV. When pressure is constant, we can write this one as d equal to U plus PV, that is d of H. So, for a constant pressure process, del Q can be represented as Cp dt to be equal to dH. That means dou H dou T at constant pressure can be defined as the specific heat at constant pressure. So, we write Cp dt plus dou H dou P at T dP. So, what we should do next, like we have done in the previous case, if you are not sure, just go to the previous slide to check. We are going to consider entropy S as a function of T and P, so that we can make use of the Maxwell's relation. So, we have ds is equal to dou S dou T at P dt plus dou S dou P at T dP. Now, we make use of the second Gibbs equation, where we have dH is equal to T ds plus V dP to get T dou S dou T at P dt plus V plus T dou S dou P at T dP. So, if you compare this expression for dH and this expression for dH, we get Cp equal to T into dou S dou T at P, or dou S dou T at P is equal to Cp by T. Again, make a note of this one we shall be using in the very first slide of the next lecture. But our interest is the second term, that is a term which is the coefficient of dP, where we have dou H dou P of T is equal to V plus T into dou S dou T at T, and we are going to make use of this particular Maxwell's relations to rewrite this as T into dou V dou T at P. So, finally, we get then dH is equal to Cp dt plus V minus T into dou V dou T at P dP, or during a particular process the change in specific enthalpy can be represented as H2 minus H1 equal to integral T1 to T2 Cp dt plus integral P1 to P2 V minus T into dou V dou T at P dP. So, again by knowing the PVT relationship of a substance and from knowledge of how specific it at constant pressure, that is Cp varies with temperature, you can easily calculate the changes in enthalpy. So, this is the second relation. Again my suggestion is try to develop this particular relation on your own by repeating this particular exercise. It would have been logical to develop the expression for changes in entropy, where we shall be making use of this relation and the one we developed in the previous slide or kept aside in the previous slide, but that I shall be doing in the next class, so that I can allow you sufficient time to develop these two relations. So, please develop these relations for du and dH and also the Maxwell's equations on your own, and also try to remember or try to find a way about remembering that Maxwell square, so that you can make use of that in any subsequent discussion. So, I would like to stop here today. Just to quickly summarize what we have done today, we have discussed about the need of developing property relations, particularly relations of changes in internal energy, enthalpy and entropy in terms of the measurable quantities like pressure, temperature and specific volume. Then we have provided a mathematical perspective of property, defined the four thermodynamic potentials like internal energy, enthalpy, Gibbs free energy and Helmholtz free energy. Then we developed four Maxwell's relations and generalized relations for du and dH, and I repeat, you try to develop this on your own, because we have done a bit of mathematics, quite simple mathematics following standard procedure, but if you are not doing that on your own, you will not be able to remember that. So, try to do it on your own before moving to the next lecture. So, that is it for the day. I would like to stop here, and in the next lecture we shall be discussing about developing the generalized relations for entropy to start with. Then we shall be seeing how to use this for certain kind of substances, and then we shall be talking about the specific heats. So, thank you.